Assalamualaikum warahmatullahi wabarakatuh. So today we are going to talk about the paper titled Behavior of 12% Chromium Low Activation Ferritic-martensitic Steel EK 181 after holding in static lead melt at 600 degrees C for 3000 hours. So as for the summary of the abstract, objective of the study investigates the behavior of low activation 12 chromium ferritic martensitic steel during holding in an oxygen containing lead melt at 600 degrees C for 3000 hours. As for the background, the development of new generation of reactors, generation 4 cooled using lead-based coolants, and low activation ferritic martensitic steels are promising structural materials to be used to that reactor. As for the experimental procedure, the experimental material was EK 181 steel with an initial element composition. The specimen were held 3000 hours and 600 degrees at 600 degrees C, as mentioned before. Results: 5 to 45 micrometer B layer oxide scale is formed on the steel surface. The outer layer is enriched with iron and the inner layer with chromium. The oxide scale is primarily represented by magnetite and wolfstite iron oxides, and to a lesser extent by chromium oxides. As for the microstructure analysis, the bulk microstructure of the steel retains its stability during long-term exposure in liquid lead. No qualitative changes are observed after such exposure. Elemental composition: the content of iron and chromium in the surface layer differs significantly from that in the matrix. A chromium depleted region several micrometers thick is found under the scale layer. Conclusion: the study demonstrates the formation of bilayer oxide scale on the steel surface and the stability of the bulk microstructure during long-term exposure in liquid lead. The chromium depleted region under the scale is observed. Let's start with introduction. The development of new generation reactors, the generation 4. Researchers are developing new generation reactors, generation 4 cooled with lead-based coolants, which are designed to be highly safe. And as for the material, low activation ferritic martensitic steels are promising structural materials for these reactors due to their ability to reduce radiation effects on the environment. One of the main difficulties in this technology, lead-based coolant, is liquid metal corrosion, which is caused by the dissolution of steel components into the coolant. As related to oxygen concentration, the character of interaction between the coolant and structural material is determined by several main parameters, including oxygen concentration in lead melt. As for related to oxide films, since steel components have higher affinity for oxygen than lead, they can form surface oxide layers, which can serve as diffusion barrier to prevent the release of steel components into the coolant. Importance of chromium content. The formation of protective oxide films with an increased chromium content is an effective method for suppressing liquid metal corrosion due to the higher thermodynamic stability of chromium oxide compared to iron oxide. And Russian ferritic martensitic steel. Russian scientists have developed heat-resistant ferritic martensitic 12% chromium steels such as EK 181 and EP 823 for application in nuclear, fast, and thermonuclear reactors. And the objective of the study is to investigate the behavior of low activation 12 chromium ferritic martensitic steel, and the aims to understand the formation of oxide scales on the steel surface, the stability of the bulk microstructure, and the elemental composition changes in the near surface layer under this condition. And As for the test material and experimental procedure, the steel type or the material is a low activation 12 chromium, as we can see from this table. So this is Fa based materials. Chromium is about 11.17, and there is content of nickel, but very small, almost negligible, and so on. And as for the heat treatment for the material, the steel spaceman underwent traditional heat treatment involving air quenching from 1100 degrees C and tempering at 720 degrees C. As for the experimental procedure, the spacemen were held 3000 hours at 600 degrees C in lead melt in specially designed sealed containers. So this is the containers, as we can see from the figure. So we call it they call it ampoule design. So it's like tube, and then you put all the spacemen, this kind of spacemen for cylindrical samples for fatigue and tensile tests inside, and they are being held using molybdenum wire, and they are surrounded by PB. So they manage to they put it inside the tube, and surrounding by that they put PB. And as for the upper part is covered by argon gas, and then it is closed and heat up to 3000 hours. And as for the lead purity, the initial lead purity was 99.98%. Oxygen concentration, the range of oxygen concentration is about 10 to minus 6 %. The sample preparation, sample were prepared for analysis by electrolytic polishing and focus in ion beam etching. As for the analytical methods, the samples were analyzed using SEM, EDX, XRG, and TEM. Okay, result and discussion. They divided into two. First, the characterization of the oxide scales, and after that, features of the spaceman bulk microstructure. Okay, so this is the SEM image of the surface of the materials, and B is the EDX spectrum. The image reveals that the specimen is uniformly covered with dispersed oxide scales. So it is covered by oxide scales, which can reach a size of about 10 micrometers. So it's like particles with 10 micrometers. And the elemental analysis, figure B, in addition to the presence of iron, as you can see here, iron, and chromium lines, shows an increased oxygen content. Yes, over here, you can see increase in oxygen content on the surface of the specimen compared to the matrix in the steel bulk. This is apparently due to the formation of oxide films on the surface of the steel. Next, figure 3 shows the SEM and the line analysis on the surface. They put several points here, 1 to up to 5. The first image, figure 3A, this one, presents a cross-section near surface, indicating loose inhomogeneous layer with thickness 5 to 45 micrometer on surface. Yes, roughly. The elemental composition at various points along this cross-section is analyzed using EDX, revealing significant differences in the content of iron and chromium compared to the matrix. As we can see here, this is the surface line, and we have the oxygen increase, and this shows increase of chromium near the surface, or on the surface, and decrease of iron on the surface. The oxygen content in this layer reach 11.3 weight%. Second image, figure 3b, shows a change in elemental composition. Yes, as mentioned before, this image reveals monotonic changes in content. The formation of B-layer scale on the surface is observed, with a small peak in the iron content in the outer layer and the peak in the chromium content in the inner layer. The chromium depleted region, several micrometers thick, is found under the layer. You can see here, this is the bulk, but under the layer, we can see decrease or depleted of chromium content. And as I mentioned before, that they analyze several points, like 5 points here, 1, 2, 3, 4, 5. Yes, 1 and 2 in the scale, 3 just below the scale, 4 also, 5 roughly in the matrix. And as we can see here, the point 1 and 2 in the visible surface layer shows a significant difference in the content of iron and chromium. You can see 1 and 2, iron, yeah, decrease of chromium here, but increase of chromium in point number 2. The iron content roughly the same. Yeah, it's decreased actually, but almost similar. The oxygen content in this layer reaches 11.3. Okay, 0.2, it's 11.3 weight%, while 0.3 and 4 and 5 refer to the subsurface layer up to 15 micrometer thick, where the contents of iron and chromium differ from each other and from the matrix. As we can see, 3, 4, 5, 3, 4, 5, it's beneath the oxide layer. We can see content of oxygen roughly the same, chromium vary, and the iron almost the same. The table highlights non-monotonic changes. The chromium content can reach 23 to 28 weight% in this layer, which is approximately twice higher than its content in the matrix. At the depth of 5 to 10 micrometers, the chromium content of 5 to 8 weight% indicating a depletion of the solid solution in chromium in this region. And this is the figure of XRD. The figure shows that the oxide scale formed on the surface is primarily composed of particles, magnetite, wustite iron oxides, and to lesser extent bichromia. The XRD analysis provides detailed information about the composition of the surface oxide layers, which is crucial for understanding the corrosion behavior. And this is the TEM result. As you can see, the figure shows series TM images. Specifically, the image reveals the formation of B layer scale on the surface, with outer layer enriched in iron and the inner layer enriched in chromium. The TM analysis also highlights the presence of chromium depleted region. And additionally, the image shows the microstructure of the steel matrix, which remains stable during the exposure. The TM examination provides comprehensive understanding of the microstructure changes and the formation of oxide scales on the surface. And this is the map analysis from the cross-section. Specifically, the image revealed the formation of B layer, as we have found before. The outer layer enriched in iron and the inner layer enriched in chromium. Yes. Yeah, the EDX examination provides a comprehensive understanding of the microstructure changes and the formation of oxide scales. And next, a result and discussion for section 3.2, features of the specimen bulk microstructures. So here, it shows the result of TEM, and this TEM shows provide detailed information of the microstructure and elemental composition of the steel. Specifically, the image reveal the formation of P-layer oxide, as we have found before. The TM analysis also highlights the presence of chromium depleted region. Additionally, the images show the microstructure of steel matrix, which remains stable during exposure, with no qualitative changes observed. So finally, as for the conclusion, the study concludes that the low activation 12 chromium ferritic-martensitic forms 5 to 45 micrometers B-layer oxide scale on its surface when held in an oxygen-containing lead at 600 degrees C for 3000 hours. The outer layer is enriched with iron, while the inner layer is enriched with chromium. This oxide scale is primarily composed of magnetite and wustite iron oxide, and to a lesser extent by chromium oxides. A chromium depleted region several micrometers thick is found under the scale layer, indicating the intense diffusion of chromium towards the oxygen-containing lead melt. The bulk microstructure of the steel remains stable during this exposure with no qualitative changes observed. The study highlights the importance of understanding the corrosion behavior of low activation ferritic-martensitic steels in lead-cooled reactors to ensure their long-term stability and corrosion resistance. As for from this study, there are several research ideas. First, investigation of the effect of oxygen concentration on corrosion behavior with similar material. Second, investigation of the effect temperature, corrosion behavior. And third, investigation of the effect of different lead melts on corrosion behavior. For example, use pure lead and in comparison to lead with some impurities. That's all. Thank you very much.